Now, the basic amplifiers are classified into 4 types. Okay. So far, we discussed only about the voltage amplifier, and in the sense, the gain of voltage amplifier is output voltage to input voltage. But in reality, you don't have to have only voltage amplifier. You can have other types of amplifiers as well. Now, the basic amplifiers are classified into 4 types. Okay, the first type is your voltage amplifier. Okay, whose open loop gain AV is given as V0 by Vi. Okay, let me just write this as open loop gain. Okay, and then we have current amplifier. Okay, whose open loop gain is taken as AI, which is I0 by II. Okay, and then we have trans resistance. In short, let me write ham, which is taken as RM, which is resistance is V by I ratio. So output entity is voltage, input entity is current. And then you have transconductance amplifier, that is denoted by GM. So conductance is current by voltage ratio, hence output entity is I0, input entity is Vi. All right. So these are the basic 4 amplifiers. Okay. Remember one thing, in this discussion, our aim is to provide an electric circuit. Okay, so our aim is to provide an equivalent circuit which talks about the voltage amplifier. All right. Now, how do you construct an electric circuit? So you can construct electric circuit based on 2-step approach. Okay, so this is the algorithm which I have derived. So first of all, you need to understand what is the gain. So it's a voltage amplifier. So gain got to be the voltage gain, which is output voltage to input voltage. Okay, so first you write down the gain for voltage amplifier. It is output voltage to input voltage. Then you just identify output variable, and then you identify input variable. Okay, so what is our output variable? Output variable is voltage, which is V0. And what's our input variable? Input variable is also Vi, which is also a voltage variable or signal, you can say. Okay, so that means to say on the output side we need to derive a voltage, and on the input side there exists an input voltage. So the equivalent circuit what we are going to choose for an voltage amplifier is the Thevenin's equivalent circuit, because whenever you have the signal as the voltage, you can go for Thevenin's equivalent circuit. On the other hand, if your signal were to be the current, then you can go for Norton's equivalent circuit. Since it is voltage, what I will do for both the circuits, okay, that is for the input circuit as well as the output circuit, keep Thevenin's theorem. Okay. Okay, so this is the algorithm. Okay, so Thevenin's theorem, or you can say Thevenin's circuit. That would be more appropriate. Okay, so theorem, let me not write. Thevenin's circuit, let me write. All right, so on the input side, let us construct the Thevenin's theorem. Okay, so what do we have? We have a source. And we have a source resistance. Source is Vs, resistance is Rs, connected to the input impedance. Okay, let's take the input impedance as Ri. All right, so that's your input Thevenin's circuit. Similarly, on the output side, let us construct the output Thevenin circuit. So on the output side, output voltage is observed, right? So what we will do, let us define the output as, you just cross multiply. So V0 is AV times VI, where VI is the voltage measured across the input resistance Ri. Okay, and then you have the output impedance, which is taken as R0, connected across the external load resistance RL. Okay, so this is your output Thevenin's circuit. Okay, now put together. What you can say is that the circuit which is found within this box, basically the voltage amplifier circuit. Okay, so this is the voltage amplifier circuit. All right, now let us derive some important parameters of voltage amplifier circuit. Okay, so what we will do is you apply voltage divider rule on the input side. Okay, so let's write an expression for VI based on voltage divider rule. So VI is equal to source voltage Vs into resistance across which voltage is measured, that is Ri, divided by sum of the resistances Rs plus Ri. Okay, then if let's say suppose your input resistance is very large in comparison with source resistance, then you would have obtained Vi approximately equal to Vs into Ri divided by Ri. Okay, that's because Ri is very much greater in comparison with Rs. So in the denominator, you can write off Ri itself. So Ri gets cancelled off. So approximately your input voltage is equal to source voltage, provided your input resistance of the amplifier is very large. Okay, so for an ideal voltage amplifier, what is that is expected? For an ideal voltage amplifier, you should have input resistance is equal to infinity ohms. Okay, that is what is expected. But in reality, you cannot have an infinite resistance, but you must design for a practical circuit, for a practical voltage amplifier. Design should be such that Ri is very large. All right, so that is what you get to know from the input side. Okay, let me just mark this result. Okay, and similarly, let me mark this result as well. Okay, fine. Now let us pay our attention to output side. Okay, output side. So on the output side, again, we have a Thevenin circuit. So let us apply voltage divider rule. Okay, to write an expression for output. So let's apply voltage divider rule. So V0 is equal to, okay, what is V0 based on voltage divider rule? Okay, this is V0. Okay, I think I did not mention this. So this is V naught. So V naught is equal to source voltage into RL divided by R naught plus RL. So V naught is equal to source voltage, which is AV into VI into RL divided by R naught plus R. Okay, so this is the exact expression. Let me put it inside the box. Right. Then approximation. Okay. Let's say suppose the load resistance is very large, okay, in comparison with the output resistance of the amplifier. If RL is, very, very large in comparison with R naught, then V naught can be approximately written as AV into VI into RL divided by RL, because R naught is very small. So this gets cancelled off. So, you would get V naught approximately equal to AV into VI. AV into VI, provided RL is very large in comparison with R naught. So in other words, what you can say is that for an ideal voltage amplifier, R naught should be 0 ohm. Correct? R naught should be 0 ohm, but which is not possible. Therefore, for a practical voltage amplifier, R naught should be as small as possible. As small as possible. All right. So this is the, you could say that performance equations of voltage amplifier circuit. All right. Now let us take the second one, current amplifier. Current amplifier. For short notes, they can ask, okay, draw the equivalent circuits of basic amplifier circuits and write an expression for input and output voltages and currents. So this is what you are supposed to do it. Okay. So that the previous one you have understood. So you can, finish off the remaining three with less time. All right. So current amplifier, let us look into. Now, current amplifier basically provides output current proportional to input current. Correct. And the gain of current amplifier is taken as AI, which is equal to I naught by I. That means to say the output signal or variable is current and the input signal or variable is also current. Since both the signals are currents in nature, okay, we go for Norton's circuit. We go for Norton's circuit since both are currents. So Norton. Okay. All right. Let's do it. Now on the input side, what you have? You have the input resistance, Ri, and on the output side, you will have a current source. This is R naught. Okay. And then, this Ri is connected to the input current source, right? So how do you represent input current source? This is the source resistance Rs. And this is your source current Is. Okay. And on the output side, you will have your load resistor RL. All right. So this is the representation of current amplifier circuit. Okay. So this is your input current II, and this is your output current I naught. Okay. You can also represent the internal parameters. Okay. So Yeah. So this is your current amplifier circuit. Okay. Yeah. This thing I forgot to mention. So this current source is AI times, okay, II. Just you have to cross multiply. AI times II. Okay. Now let us apply the write down the performance equations. First, let us take input circuit. Okay, since we are dealing with the currents, so we can apply current division rule. So apply CDR, current division rule. Okay, in short, current division rule. Okay. I'll write it off. Current division rule. Okay, fine. So what is it? You want to find II, right? So branch current II is equal to main current IS into resistance of the opposite branch, that is RS, divided by sum of the resistances. So this is your exact expression for the input current II. Okay, all right. Now we can apply the approximation. So in the approximation, what if your input resistance were to be very small in comparison with RS? Or other words, you can say, what if your source resistance were to be very large in comparison with the input resistance R? Because for an ideal current source, the shunt resistance should be infinite, right? So if that's the case, your input current II can be written something like IS into RS divided by RS. That's because RI is negligibly small, and therefore you will get II approximately equals to IS itself. Okay. IS itself, provided your source resistance is very large in comparison with the input resistance. Okay, so that's from the input circuit. Then let us obtain some relationship from the output circuit. So let us go to output circuit. Okay, what do we have at the output circuit? So on the output circuit, okay, you can see that current I0 is flowing through the load resistor RL. So we can write an expression for I0 using current division rule. So once again, let me write, apply current division rule. Okay, so I0 is equal to source current, which is AI times II, right, into resistance of the opposite branch, which is R0, divided by R0 plus RL. Okay, so this is your exact expression. Okay, approximation. Okay, what if your RL were to be very small in comparison with R0? Or in other words, what if your output resistance R0 were to be, very large in comparison with the load resistance RL? Okay, if that is the case, you would have got I0 approximately, equals to II into AI into R0 divided by R0. So going to get cancel out, hence you will be left with I0 approximately equals to II. Okay, so that's your approximate expression. So note. So in note, what you can write is that for an ideal current amplifier, okay, for an ideal current amplifier, Ri should be infinite. Sorry, not Ri, I'm so sorry. Yeah, Ri should be 0. Okay, Ri should be 0 and Rs should be infinity, 0. And R0 should be infinite. R naught should be infinite. Okay. On the other hand, for a practical circuit, for a practical current amplifier, okay, design should ensure that Ri is very small and R naught is very large. All right. So that's about your current amplifier. Okay. The third one is transconductance amplifier.
Sir?
Yes, yes, tell me.
So for the output part of the current amplifier, it should be I naught approximately equal to the gain part, no, sir?
Yeah. This one, right? It should have been AI, correct, no?
Yes, sir.
I missed it. Yeah, thank you. Yeah, correct. Fine. Next is transconductance amplifier. Okay. So in case of transconductance amplifier, in order to construct the equivalent circuit, first you write down the gain expression. So conductance, right? Conductance. How will you find conductance? By taking out the ratio current by voltage. Okay. So this gain, let's take it as GM. Okay. Conductance we will define by a capital letter G, right? So what is your output variable? So output is current, correct? And your input is voltage. Okay. So on the output side, you should have a current. That means to say output should be drawn with the help of Norton's circuit. And in the input side, you have the signal as the voltage. So you have to have a Thevenin circuit on the input side. That's how we construct the basic amplifier circuit. All right, so let's go ahead with the construction part. So in the input side, you need to have a Thevenin circuit, right? So let's draw the Thevenin circuit. Your input resistance Ri connected to source voltage having a source resistance of Rs. This is Vs. All right. This is your input current II. So that is your input side Thevenin circuit, and this is your Vi. Okay, and on the output side, what do you have? Your signal is current, so you should have a current source. Okay, and what is that current? So this is I naught by Vi. Okay, so current I naught is equal to Gm times Vi. So this is Gm into Vi, and then you will have the output resistance R naught. Okay, connected across the load resistor RL. All right, and this is your output current I naught. Fine. So this is your trans resistance amplifier. Okay. All right. Any doubts? I'll just pause for a while. Any doubts? If you are clear about how to construct these equivalent circuit, you can quickly type yes in the chat box. Okay, fine. Even one yes will do for me. All right, yeah. All right, so let us apply the analysis now. Input side. So input circuit. Okay, since on the input side you have voltage, so let us apply voltage divider rule. Okay, apply voltage divider rule. So VI is equal to source voltage into RI divided by RS plus RI. So that's the exact expression. Okay, and approximation. If Ri is very large in comparison with source resistance Rs, then you will get Vi approximately equals to Vs into Ri by Ri gets cancelled. That implies Vi approximately equals to Vs. So for an ideal transconductance amplifier, your input voltage should be very close to the source voltage. Okay, should be very close to source voltage. Okay, the note part I will write it in the end. Now let me take up the output circuit. Output circuit. As we know that on the output side we have current signal. So let's apply current division rule. Apply current division rule to get the value of I0. So I0 is equal to main current. Okay, so main current is the source current times the resistance ratio, right? So source current is Gm into Vi, correct? Yeah, Gm into Vi into resistance of the other branch, that is R0 divided by R0 plus Rm. So this is the exact expression for the output current. Okay, and approximation. So if we were to consider, the output resistance of the amplifier were to be very large in comparison with the load resistance, then you would have obtained I0 very close to Gm into Vi. Okay, that's because R0 by R0 ratio going to get cancelled, and due to which you will get I0 is equal to Gm into Vi. Okay, so this is the approximate expression. Okay, so all right, so what we have done is we have written exact expression as well as approximate expression. Okay, hence you can summarize with a short note. Okay, so for an ideal transconductance amplifier, your input resistance should be very large, or Ri should be infinite. Okay, on the other hand, R0 basically Ri should be very large, so Ri should be infinite, and R0 should be very large in comparison, so R0 should be infinite as well. Okay, all right. On the other hand, for a practical circuit, here itself, let me write, for a practical circuit, Ri should be very high, and R0 should also be very high. So put together, I can write it, right? Fine. So this is your transconductance amplifier, and finally you are left with trans-resistance amplifier. Resistance. Okay. Fine. In case of trans-resistance amplifier, gain, we shall take it as Rm, because we're talking about the resistance gain, right? I mean, the resistance term is involved. So Rm, what is resistance? Resistance is the ratio of voltage to current, right? So this is your output signal, which is voltage, and this is your input signal, which is current. That means to say, on the output side you should have Thevenin circuit, and on the input side you should have Norton's circuit. conductance circuit. Okay, so we can build the circuit now. First, let us draw the amplifier. This is your Ri. Okay. So on the input side, you have Norton circuit, right? So fine, Ri, and this then gets connected to the source resistance, and then comes the source current Is. This is Is, and this is IL. All right, and on the output side, you have the gain part. Okay, and the output source, right, which is a voltage source. So you can represent V as Rm times I. So this is your V0 and this is your II. So it is Rm into II. Okay. Then comes the output resistance R0. And later on, it is connected to the load resistance RL. And across the load, we have the output voltage V0. Okay, so this is our equivalent circuit. All right. Next, let us write down the performance equations. Input circuit. Since on the input circuit we have current, so let us apply what rule? Current division rule. So you can write II is equal to source current into opposite branch resistance divided by sum of the resistances. So that is your exact expression. And for approximation, you can write if your source resistance is very large in comparison with Ri, then the input current II will be very close to the source current, because Rs and Rs is going to get cancelled out. Hence, you will have II very close to Is. Okay, so that's your approximated expression for the input currents. Okay, next you can apply the network reduction rule in the output circuit. So let me write output circuit. Okay, so output circuit, you have a voltage source, hence let us apply voltage division rule. So V0, let us write, so V0 is equal to source voltage